Hello everyone, in this video I'll introduce our work, MoTIF Learning Motion Trajectories with Local Implicit Neural Function for Continuous Spacetime Video Super Resolution. This work addresses continuous spacetime video super resolution that aims to upscale an input video both spatially and temporally by any scaling factor with only one model. One of the key challenges in this field is to propagate information temporally among the input video frames to any target spatial temporal location. To this end, we introduce an implicit neural function to model motion trajectories of pixels. In this work, we propose a space-time local implicit neural function that predicts forward motion and its reliability in a continuous manner. To fuse information from multiple reference frames, we propose a reliability-aware splitting and decoding scheme. Experimental results demonstrate that our MoTIF achieves a state-of-the-art performance on continuous spacetime video super resolution and is capable to any number of reference frames. Here is a system view of our MoTIF. Given two low-resolution reference frames, our task is to interpolate a high-resolution video frame with any arbitrary spatial scale at any time t. To achieve this, a spatial local implicit neural function first super-resolute the low-resolution input frame to high-resolution feature. For the motion part, we first compute the optical flow maps and the corresponding reliability maps of two reference frames. After that, a spatial temporal local implicit function renders a high-resolution forward motion map and its reliability map. At the end, we adopt forward-warping, reliability-aware splitting and decoding scheme for fusing spatial temporal information from multiple reference frames. In this paper, we try to model motion trajectories of pixels by an implicit neural function. In the case of backward motion, the backward motion vector at P2, when viewed as a function of time, are a mixture of multiple motion trajectories. This could potentially introduce undesirable randomness and discontinuities in the resulting time function. In contrast, the forward motion vector at P2 in individual motion trajectory, which means that forward motion typically forms a smoother space-time function. Thus, we adopt forward motion rather than backward motion in this paper. Given the reference low-resolution motion feature, our space-time local implicit neural function takes the nearest reference motion length, spatial distance, and temporal distance between the reference and target location to predict the high-resolution motion and the corresponding reliability map between the reference time tr and the target time t. To fuse spatial temporal information from multiple reference frames, we adopt forward-warping reliability splitting. For multi-frame forward-warping, PowerWorks adopt the single-frame softmax splitting to warp individual motion fields. In contrast, our MoTIF performs joint multi-frame softmax splitting for frame interpolation. From the perspective of single reconstruction based on irregular taken samples, our joint sampling considers all rather than partial samples in the splitting and reconstruction process. This table compares the computing method on the continuous spacetime video super resolution task with different spatial and temporal scale. As shown, MoTIF achieves the best performance in all the test cases. This slide shows the subjective quality comparison of continuous spacetime video super resolution method. We can see that our MoTIF preserves more high-frequency details than the other computing method. For example, the head of the dots. Thank you for your attention.